Hello, ToobTimers. Welcome back. This is the last session of the passive testing and examination of the 6P1. Today we're going to look under the hood and see what we can see. Now I have removed many of the screws and nuts just to save time and not to fiddle with screwdrivers and whatnot. So here we go. Let's take the back open and see the wonders that are inside. Ooh, wonderful. Okay, what do we have here? Let's talk about several good things and several things I don't care for. First, what's really nice is the welded edges. I'm not sure if you can see it on the camera, but each one of these corners are very nicely welded into place. They folded the box up and welded it for strength and rigidity. The overall wiring looks very good. I don't see too many cold joints. The components are recognized. These are Vichy capacitors. Other components, I recognize their names. NXB capacitors. Let's see what else is in here. Oh, well, let's just take a minute and talk about what else we can see. All right, so what do we have? Back here is the input socket with the fuse. Very good. A little fuse to protect an overload. Absolutely essential. The ground is bolted very nicely to the case with a, looks like a Loctite bolt, which is perfect. This is the power transformer. So this input part goes to the power switch right here. And it's kind of fascinating to see because we all know that blue light that's on front. Well, look how they've mounted it. Very clever, very economical. What they've done is they've taken the LED assembly and wire tied it to the switch body at the right height so that when you stick the switch in, the little blue LED pokes out. That's kind of cool. I think I'll replace it with an orange one or something less in your face. Blue is a very popular color for these kind of things, but not for me, and not for this application. As you can see, I've removed many of the nuts and bolts that hold the thing together. There we go. This is the switch that scared me out of the very first episode or second episode. It is the headphone main speaker switch. The hole in the chassis that this switch mounts into doesn't go. It's actually threaded, which is a testament to the thickness of this chassis. I think I'll taper it out a little bit with a reamer so it goes in and out a little more easily. Having said that, I believe that looking at this switch, unlabeled by the by, the headphone jack and the impedance network, which is back here, I believe the headphone jack is a bit of an afterthought. It's not tacked down like everything else is so nicely. You have flying components, which I am not a big fan of. They can kind of jiggle around and get into places they oughtn't. Other than that, it looks pretty good. Again, the copious use of heat shrink tubing is a sign of a good quality build. You haven't got bare parts sticking around to be touching. So as we go in through this power switch, it energizes this power transformer, which on the reverse side is that large center transformer. Here is a choke, which helps to smooth out the DC. This particular tube is the rectifier, and you can see the red lead that comes right up to this 150 microfarad capacitor. Too big. Too big. This tube wants 4 or 5 microfarads on the output maximum. Apparently, the internal wiring can't handle much more of a reservoir size than 4 microfarads. So to place a 150 microfarad capacitor in there is just going to shorten the life of the rectifier tube. It goes from the rectifier tube to the capacitor, to the choke, and then back to this capacitor again, the second bulk capacitor. This is 150 microfarads, and it can perfectly well stay 150 microfarads. After I change this down to 4.7 microfarads, I'll give it a listen for hum. If there's some hum I can detect, I will try to replace this capacitor or perhaps replace this inductor. The inductor looks like it's a 5 Henry 100 ohm inductor. It would be hard to go higher without dropping the voltage. But this is something very interesting that happens. The choke goes to this capacitor, which then comes down to this little tag board and goes to a split resistor, kind of a T configuration. Now that's fascinating because I don't see this very often. They're trying to take the right and left channels and separate potential crosstalk or interference by putting a resistor here. And then on the output of the resistor is another bulk capacitor, which helps store the energy for the deep bass and high levels of bass. Very good. It's a very, very good thought. I'm kind of curious to see how that actually works with a voltage meter. The tag board is very nice. All the components are on the tag board. The amplifier is very well designed, as it is split down the middle, the left side and the right side. So I can work only on this side and work on the left channel, or work only on this side and work on the right channel. Now the power supply, of course, it doesn't apply because there's only one of those, but even it is somewhat symmetric on the layout. Very, very good. I like that symmetric layout. This is very cool. Okay, so now we've got power to our tubes, plate power, through this bulk capacitor. We go through a voltage dropping resistor, and look, we've got a coupling capacitor. It's a 300 nanofarad capacitor, a 0.3 microfarad, and this MKP, I don't think you can see it. Maybe I can zoom in on it a little bit. The MKP is a propylene dielectric, polypropylene dielectric. No, you can't even really see it. It's really fine black print. Polypropylene is my favorite dielectric for capacitors. So I thought I was going to replace the coupling capacitors. I'm just going to leave it alone. Let me make this one point perfectly clear. You've all heard the saying, you can't make a silk purse out of a sow's ear. What that means is if you don't have the right materials for a design, you can't make it something that it isn't. Now, this is an absolutely fine tube amplifier, but I wouldn't want to turn it into a $1,000 Marantz. That would be just throwing money away. So we're going to attempt to make this amp perform as well as it can with a minimum amount of component investment and see where it goes. This tube right here is the 6SN7 tube. It is the pentode simulator. The triode sections are connected in a cascode fashion, and the grid of the second tube acts like a screen. That's the fixed resistance right here that I want to change and turn it into a fixed voltage instead of a self-biasing tube stage. These two capacitor resistor parallel combinations are the bias setting resistors for the grid and the AC bypass using the capacitors. If you don't bypass that resistor for setting your bias on the cathode of the tube, it will change bias depending upon the signal level that's going in, and no one's going to thank you for that. So we've got this bypassing network. Then let's see if we can find right under here. Let's see if you can see it on the screen. Well, under there is a pair of tubes. There's one here and one here. These are the output tubes, the 6P1s, if you will. They're the tubes that drive the output transformers, which you can't see because they're on the underside of the chassis, or the top of the chassis, and they flank both sides of the power transformer. So as I'm looking at this, I'm looking, well, you can really do something with this amplifier. It's easy to work on using the tag board. A couple of simple changes, and you'll have a nice sounding amp. All the parts are isolated from the chassis, which will allow me to make some star grounding schemes. A star grounding scheme is where you don't run the common from tube to tube to tube to tube. You pick a point, generally the common of the power filter capacitors, and every time you encounter a common, a ground, if you will, you don't take it to the ground, you take it to this point. And by doing that, you have a tendency to reduce ground loops, which improves the noise level of the amplifier. It reduces your noise floor. Now, let me be very specific about this amp. I'm going to clean it up, test it, burn it in for about 40 hours, and then I'm going to sell it on eBay or whoever sends me a shout out in the comments section. I didn't buy this amp to keep for myself. I bought it to improve and then resell. Oh, I've almost forgot the VU meter. Here's the VU meter as it comes out. I've removed the screws. The VU meter, let's see if we can see what's going on back here. It's kind of hard. Everything's black, and so it's very hard to illuminate it properly. But if you can see this orange and brown wire, these wires provide the power to that very nicely colored lamp. These two contacts provide the signal to the VU meter. You've got an AC capacitor to get unwanted AC signals off the meter, keep it off the meter, and also give it a measure of surge protection. And then in here, under this heat shrink, you've got a resistor that sets the scale readings. That's why we got such a nice scale reading of 0 when we began to get in distortion. I intend to eliminate that distortion and move it up a bit. I will definitely have to change that resistor to mount to reflect my change in distortion level. Okay, so what are we going to do to this amplifier? First thing I'm going to do is put a line cap here. A line cap or safety cap shunts high-frequency noise before it gets into the amplifier. Very good in this day and age with all the various electronic things we have. I am going to set the screen voltage at the appropriate level. We're going to do star ground wiring. How many times can I say that, eh? We're going to separate the earth chassis. So this chassis will only be at earth, a safety ground. I have not decided whether I'll put a switch in there to bridge the common to the chassis, because sometimes other pieces of equipment like that to prevent hum. I probably will. I'm going to verify the pin voltages of all the tubes. I'm going to document what they are, and I'm going to make sure that we're not getting into any near to the design max of the components. I am going to verify pin voltages at 120 and 110 volts. This is a 110 volt device. in theory, we should get plus minus 10% on this thing. But boy, 10% takes us right up to 6.9 volts on the filament, and that's dangerously close. As I look in my workspace here, I see I'm at 123 volts, and that would probably take us to 7 volts. Now, 7 volts is a bit of a magic value for 6.3 volt tubes. That's when you start really wearing them down. So I'm a little concerned about that. Not sure what I'll do about that just yet. I am going to stick SN7s into the sockets and ship it that way. I will also ship the original tubes that came with it, so you can try and see what it does. I don't think it'll do any real harm to put the original tubes back in. I think they'll just have a lower life. Oh, one other thing I'll probably do is purchase a thermistor. Now, a thermistor has what they call a negative temperature coefficient. So you put that in series with your hotline, and when you first turn the unit on, it has a high resistance. And then as current begins to flow through that thermistor, it begins to heat up and the resistance goes down to a lower level. Something that will, and that too will help keep our input voltage down. The thermistor is used to prevent inrush currents. Your filaments are your weakest when they're first turned on and before they're heated up. So have you ever noticed with a light bulb, when you first turn it on, it goes pop, and that's usually when it blows, unless someone thumps it once. That's because of the inrush current. The lights, as they age, the filaments get smaller and smaller, and you get to a certain point where that filament can't take the inrush anymore, and you blow the light bulb. I like to avoid that with our filaments, so we'll put a thermistor in there. As a side note, they used to sell these little nickel-shaped wafers that had a thermistor in them, and you would stick it in the socket of your light bulb, and it was supposed to improve the life of the bulb. It certainly did, but I think there were some issues with the thing overheating in the socket, because thermistors do get hot. Man, they're supposed to. This is a curious thing I've noticed. These are safety capacitors. These are UL safety capacitors. You can usually tell by the box it comes in, and they're called such because if the capacitor shorts out, this box is supposed to contain the mess until the fuse blows. And it's used, that's the type of style of capacitor I'll use on the line input. It also is an MKP or polypropylene dielectric, so I like that. Well, tube timers, I think we're coming to an end of this particular session. It will be about a week and a half to the next session, because I will have made all my modifications. I will have modified the left-hand side for all my change mods. And then we'll compare it, we'll listen to it, we'll measure it, and then we'll compare it to the right side, and we'll see if we have actually done improvement. Oh, poop. Always happens. You wiggle things around and a wire breaks off. Fortunately, only one broke off, and I can see it goes back here. That's not a big deal, just a touch of solder. Always happens with a wire, so you always want to handle them carefully. Apparently, I've manhandled this switch, and have I have soldered again. All right, tube timers, take care, and please take care of yourselves. Please subscribe to my channel. I'm retired, so I'm looking for sources of income, and maybe I will get a penny or two from YouTube every time somebody views one of my videos after I hit a certain level of viewership and membership. So please subscribe, and we'll see you in about a week and a half. Take care, all.